So once I obtained a closed solution, I can say, let me consider now. I have an idea that one of my sets can be close to 79 over 14, but not exactly this value. So what can I do then? I can say, let me decompose my ratio, which is to have integer factors of 180. I can decompose it, okay? So I can decompose it. I can see that 180 can be decomposed into 2 times 2 times 3 times 3 times 5, okay? And I will try to, I want to select 3 sets, and I can try to have the 3 sets as close as each other. Yeah, here, if you take 2 times 3, you get 6. If you take 2 times 3, you get 6, and you have 5. So you can write 180 in the form of 5 times 6 times 6. Always, whenever you decompose a number into multiple factors, and you have a number of sets to consider, try to take the sets numbers close to each other. And you can have selected the following combination. You can say, I can take also 2 times 5, which is 10, and 2 with 3, which was 6, and then I will be left with 3. So you can design another possibility where the 3 sets have different ratios of 3, 6, 10, but it's advised to have the ratios as close as possible to each other, because larger the ratio, the operation is not smoother, because we have seen that the maximum ratio allowed is 10, and it's good to keep smaller ratios as much as possible, okay? In this way, the sizes of pinion and gears will be closer to each other, which is better. So now, this is the best combination to select to have if 3 sets and a total gear ratio of 180. So since now we have seen that we already designed a certain number of teeth of the pinion equal 14 is a good choice, okay? So you can say that now, if I take 3 pinion of 14 teeth, then I should have for my gears, okay, for one, it should have 14 times 5 teeth. And for the 2 other sets, they should have 14 times 6 gears, okay? So for my 3 pinions, I take them identical with number of teeth equal to 14, because this will, if you want, allow me to avoid to have a lower possibility of interference. And then when I do my calculation, I check that to have a gear ratio of 5, I should have one of my set with 70 teeth, while for a ratio of 6, for the 2 other sets, I can have 84 teeth. And in this way, the sets are not similar, not identical completely, but they are close to each other. And I can verify in my interference table that these sizes are convenient. Okay. In general, they should tell you all conditions. They should tell you I cannot allow interference. So you should check then if there is interference or not. To check it, you go back to your table of interference and you look for 14 pinion teeth for the pinion and 25, let's say, degrees pressure angle. What is the maximum number of gears without interference? And then if it's if they satisfy, if this number satisfies the non-interference condition, you can say it's fine for me. If not, you should try other combinations if you should not have interference. Sometimes you can allow interference. It depends on the application. Okay, so depending on the given, what are if you want the conditions, they will tell you no interference is permitted. For example, they can tell you I can allow a certain maximum number of pinion teeth equal to this number. So they can add any constraints, more constraints. This will limit the possibilities in your designs. Any question on how we selected the different sets to reach a ratio of 180? Okay. So you can verify now with the 3 sets we have now that the gear ratio, as we said, is equal to the product of the driving gears, a number of teeth of driving gears, over the product of number of teeth of driven gears, and you can verify that this is the value desired for my MV. Now, another example. So here again, here this is the representation of the sets you selected. Okay, if you want to represent your final sets, this is how you can present them. So you have here 3 sets, as we mentioned. So this is your first set. This is your driver, your main driver gear, number 2, which is connected in general to a motor. So you can impose omega n. Okay. And now we have seen that the 3 pinions of our sets will be characterized by 14 T's. So you can just put here the symbol of 14T, meaning that you have 14 T's. We have seen that you have 2 identical sets, 14 with 84 for the gear. So 2 and 3 will make the first set. And now 3 and 4 will be connected to the same shaft. So they have the same angular velocity. 3 will be a driven gear, and 4 will be a driving gear for 5. So your second set will be 4 and 5, with also 14 T's and 84 T's. And finally, the third set, which is a little bit different, is characterized by a pinion of 14 T's and a gear of 70 T's, because the ratio is different than the other. It is characterized by a ratio of 5, because we were able to divide 180 into 6 times 6 times 5. So 2 of the sets will have a ratio of 6, and the other one will have a ratio of 5. Okay, and now it depends if you want to have the ratio 180 over 1 or 1 over 180, you can reverse the input will output. And here, if you want to reduce the angular velocity, 2 will be your input, 7 will be your output. If you want to increase the angular velocity, you should reverse. And your input will be here, and this is your output. And of course, when you reverse input and output, the gear ratio will be reversed. Okay, and you can have the profile presentation here. You can see that for the input shaft, I have just one gear on it. For the output shaft, I have 1 gear on it. And for intermediate gears, you will have on each shaft 2 gears, one that is driven, one that is driving. Okay, and in total, you can say that the gear ratio for the system is the product of number of T's of driving gears over the product of number of T's of the driven gears. Okay, and to know if the angular velocities are same direction or opposite direction, you should look at the number of sets. If the number of sets is, so when you have an even number of sets, you will have same angular velocity direction. However, when you have an odd number of sets, the angular velocities will be of opposite direction. So you can check here, I have 3 sets, set 1, set 2, and set 3. So since I have 3 sets here, I expect that the angular velocity of the output is opposite to the angular velocity of the input. And you can see this. So omega n opposite to omega out. And you can verify this from your calculation, because the gear ratio will be negative. Okay, so here you have a counterclockwise rotation. Here you have a clockwise rotation. And you can see this in your calculation of MV. So MV is, you have -1 to the power 3 times product of number of T's of driving gears over product of number of T's of driven gears. So since you have 3 sets, you have then in total -1 to the power 3, which is negative. And this is why you will get in total a negative gear ratio. Okay, any question on this? The person who asked me about the problems, are you still with us? Concerning the 2% increase in center distance, so that I explain it to you. Okay. Any question on this or on any other problem we did before? If you need anything, you can contact me anytime. You can open a Zoom meeting to answer your questions. Okay. Yalla, see you next time. Bye.
Thank you.